From the earlier example on the exponential random variable, hopefully you have seen that the inverse CDF method works quite well. In other words, the samples that we generated using these procedures seem to indeed follow the exponential distribution with lambda equals to y. So, why exactly does this method work? In this subsection, we will supply a theorem that explains the mechanism behind the inverse CDF method. And this theorem is known as the probability integral transformation theorem. It states the following. Suppose that a random variable x has a continuous distribution on the interval AB with CDF large F of x. Let's further suppose that the CDF fx is right continuous so that the inverse of the CDF f inverse of x is well defined on the interval from 0 to 1. Let's further assume that there is a uniform random variable between 0 and 1. Then a y, which is equal to f inverse x of u, can be shown to have the same distribution as x. You can see that here, y, which is equal to f inverse x of u, is equivalent to what we have obtained earlier in step 3. So the f inverse x is equivalent to the h function, and you can see that y is the output of applying this function to the value u. So why exactly does y obtained this way have the same distribution as the original x? Let's see a proof for this. In order to show that y has the same distribution as x, it suffices for us to show that y and x have the same CDF. In other words, fy of y is equal to fx of y for any possible y value. So let's see what fy of y is equal to. By the definition of CDF, we know that fy of y is equal to the probability that the random variable y is less than or equal to the small y, which is a constant. And now let's substitute the y over here with f inverse x of u. So by the fact that y is equal to f inverse x of u, we know that the earlier thing is equal to p, that f inverse x of u is less than or equal to y. In other words, the transformation applied to the uniform random variable u is less than or equal to y. If we apply the fs function on both sides, so on here and on here, we know that the former one is equal to the probability that u is less than or equal to fx of y. Now, note that this is the CDF of the uniform distribution. And we know that for the uniform random variable between 0 and 1, fu of x is equal to x itself. So we can exclude all these parts about pu less than or equal to, and just pull out what's in the parentheses. So we know that this is equal to fx of y. And that concludes our proof, where we can see that fy of y is equal to fx of y for all possible y values. In other words, the y obtained this way has the same distribution as x.